So it turns out that we can use the sort of idea of what it is in our previous videos in this sequence to attacking first order autonomous equations. So recall, autonomous equations are ones where you don't see the independent variable lurking in any significant way in the equation. A really good example, and my go-to example of a first order autonomous equation, is the exponential growth equation. And what we're going to do in this video, among other things, is learn how to finally actually come up with that general solution to the autonomous growth equation. So, yes, first order autonomous equations. So these are, if we're going back to the framework that we talked about earlier for first order differential equations more generally, a first order differential equation you very often can write y prime equals f of x y. Some complicated expression involving both x's and y's is that what this is, right? But in the case where we're talking about autonomous equations, we shouldn't see any x's. So we can say that a general form for a first order autonomous equation is y prime equals f of y only, no x's. Huh? Okay. Well, don't forget what y prime is. Can I rewrite y prime, please, using my favored notation for the derivative? I'm going to write it using Leibniz notation. dy dx equals f of y. Yeah? All right. So don't forget what dy dx means. Dy dx is the rate of change in y per change in x, right? What if I was to do the following thing and ask you to consider, does this make sense? Dx dy. This is under our interpretation, this would be the rate of change in the values of x as y changes, right? Another perspective on this. The way, remember, we connected in our single variable calculus class, in our first semester calculus class, we connected the idea of an instantaneous rate of change with the slope of tangent lines. So when we had the graph of a function like y equals, if we have something like y equals f of x like this, then we said something like, if this is some point along the curve, we could take a tangent line to this curve, and we interpreted the slope of that tangent line as representing this instantaneous rate of change, how the values in y were changing at this particular point x, right, and per unit change in x. Okay. But what if I asked about dx dy, how x changes as y changes? I mean, we could just as well zoom in on this picture around this point, and we'd still see the curve being very, very well approximated by this line. But if we think of y as being the independent variable, and we think of x as being the dependent variable, then using this tangent line slope interpretation, and using some geometry, we will see that dx dy is 1 over f of y. I can justify this in other ways too. This is really a consequence of something that we learned about where you take derivatives of inverse functions. This is something that I cover in my first semester calculus class, but there is a formula for the derivative of an inverse function of f inverse of x when f inverse exists, which is 1 over f prime of f inverse of x. I think that's what it is. I think that's right. Yeah, that's right. And this really follows from the chain rule. It's super easy from the chain rule. In any case, if that's for you to review, if this is something that you're interested in, just believe me that dx dy is naturally 1 over f of y. Now, comment. I want you to notice. Look here and look there. It feels like I started with this equation, which is my given autonomous differential equation, and I took the reciprocal of both sides. And that in particular, I treated this dy dx kind of like a fraction. And its reciprocal is precisely dx dy, if I view it as a fraction. Now, your other calculus instructors their brains might be melting because they tell you, do not interpret Leibniz notation as a fraction. And just tell them to relax, okay? Because in this particular situation, everything works fine. It works beautifully. Does it always work like a fraction? The answer is no, but that's okay. Here, I'm telling you it's okay, and I'm right, and so you should feel okay about working with it as a fraction in this particular context. And we're going to see other contexts where we can do exactly the same thing, treat it as a fraction. In any case, what this rewrite allows us to do, and passing from here to here, what this allows us to do is use the technology that we've had in the previous videos to finding a general solution to this differential equation. It is x as a function of y is equal to the integral of 1 over f of y dy. And this is the general solution. Now, there's a downside to this general solution, which is that our goal was to figure out what the solutions to this differential equation were, this autonomous differential equation. We wanted to find, in other words, all functions y which satisfy this relationship. But here we have y all tangled up in this integral. So if we really want to understand these solutions and this equation as it's presented, we'll want to try to solve for y. Okay, I'm being very abstract. Let's bring it down to earth with a very specific example. Let's look at the exponential growth equation. Y prime equals ky. And here I'm going to assume that k is a non-zero constant, okay? K non-zero. I could assume it's positive. You know what? No, I can't. I want to be more general than that. Let's assume k is not 0. And maybe can I just make the comment, if k is 0, then this is the equation y prime equals 0. Okay, and when is the derivative of something? When is the derivative of y equal to 0? When y is a constant. Okay, so, all right, great. But I want to use this technology that we've just developed to attacking and killing this. I'm going to rewrite this differential equation as dy dx equals 1 over ky. Okay? Then I'm going to integrate both sides with... wait, I messed up. Let me back up. I got ahead of myself a little bit. This is all wrong. Dy dx is equal to just ky. Sorry. If I had time in my life, I would have would edit that part out, but I'm just going to leave it. It's good for you to see the kind of boneheaded mistakes which can arise. Sorry. This is correct. So dy dx is equal to ky, and all I've done is rewrite y prime using Leibniz notation. Now I'm going to do the reciprocal trick. Dx dy is equal to 1 over ky. So that x as a function of y is equal to the integral of 1 over ky dy. This is my general solution. This is child's play because I can pull out the 1 over k, it's a constant. I can integrate 1 over y, and I get the natural log of the absolute value of y, and plus c, right? Plus an additive constant of integration. But for reasons that are known to me and not to you quite yet, I'm going to instead of calling the constant c, I'm going to call it d. It's a donstant is what it is, not a constant. It's an additive donstant of integration. Donstant's not a word. Don't embarrass yourself by using that out loud. It's my idea of a funny joke, okay? All right, so we have this. We have that x is equal to 1 over k natural log of the absolute value of y plus d, what I want to do is solve for y. So I'm going to start with this equation. I'll just rewrite it. The equation is x is equal to 1 over k natural log of the absolute value of y plus d. I'm going to solve for y now. Ready? I'm going to multiply both sides by k, subtract d. So kx minus d is equal to the natural log of the absolute value of y. How do you undo a natural log? You use the exponential function on both sides. Apply it to both sides. So we get that e to the kx minus d is equal to the absolute value of y. Before I do anything else, I'm going to manipulate the left-hand side and rewrite it as e to the negative d times e to the kx. Now observe, e to the negative d out front. That's a number. That's a fixed value. It doesn't depend on x in any way, right? And d is a totally arbitrary value. It could be negative, it could be positive, whatever. But the thing that I want you to acknowledge is that e to the negative d, there is something that we know about it. Because this number is being stuck into the exponential function, we know that it's going to be positive, strictly positive. And this is because the exponential function only takes on positive values. Its graph lives entirely above the x-axis. So this is a strictly positive number here. Strictly positive. Okay, but we have the absolute value of y on the right hand side of the equation, yes? And so how do you solve something like the absolute value of y equals 5? Well, what that means is that y's distance to the origin is 5. There are two ways for that to happen on the real line. Y could be either plus or minus 5. So in solving this equation, going back to our problem here, in solving this, we learn that y, and can I write it in the other order? It just makes me feel better about myself. Y is equal to plus or minus e to the negative d times e to the kx. Okay? Now, I want you to think about this number. Oh, I don't know why I did that. I want you to think about this number. Plus or minus e to the negative d. What can you say about that number? You can say that it's not 0. That's what you can say. It's going to be positive if we take the positive branch of the square root, positive branch of this solution, and it's going to be negative if we take the negative branch. But it's not going to be 0. Okay? But will you notice that y equal, if it was 0, just imagine it was 0, it would also be a solution to this differential equation. Y equal to 0 solves this differential equation, okay? So what we can do is replace this ugly looking, well, this thing here, we can replace it by just a constant. And let's call that constant c. Why c? Because c is the first letter of the word constant. That's why. So we get that y is equal to c times e to the kx. And this is how the general solution to this differential equation is developed and derived. Okay? And you can attack and kill other autonomous first order differential equations using this technique. But at the very least now, we've justified for ourselves using this what the general solution to the exponential growth equation is. Okay? All right, that's enough for today, and that's enough for this session. So long.